Have you ever shot a group and you know you did your part? Trigger squeeze seemed just perfect, sight alignment just perfect, and yet when you look downrange, you can see that that round flew off. We call them flyers, and they are the bane of the shooting world. This is an example. Nice 4-shot group right over here, and then a flyer off to the side. That happens to me with some frequency, and I've always wondered why that is, and how can I deal with that? I mean, if I know that I messed up the shot, I pulled it low, I pulled it left, right, whatever, that's one thing. I can circle that round, I called that one, and then I can simply measure a 4-shot group, and that's okay. But on those flyers where we don't understand or don't know what is going wrong, and so we go ahead and measure a full 5-shot group, it doesn't look very good, and it probably is not representative, truly representative, of how well that rifle or that round or that load was shooting on that particular day. So I've been thinking about this for quite some time, and what I have done is I have developed a new or alternative way of measuring our groups to better understand how the group or the load is actually working and take into account those flyers and allow us to statistically eliminate those flyers when compared to the rest of the group. And of course, it's very easy to say, no, that's a flyer, I'm just going to call it and get it out of here and throw it away. You can do that, but sometimes it's not so much of a flyer, and we're like, I don't know if I should include that or not. And you want to be fair with it because you want to make a fair comparison between one load and another, or one bullet and another. And so what I have done is come up with this alternative way of measuring groups. What we're accustomed to doing, of course, is measuring the extreme spread, which is always going to include that flyer, and then converting the extreme spread in inches into MOA. This 5-shot group here, shot at 200 yards, gave me a 1.52 MOA. But my approach now is to take this group, and what I'll do is I'm going to use a computer to help do all these calculations, but in essence, I am connecting the dots to make a perimeter or boundary around these 5 shots. The shape of that is going to be essentially a polygon, and we can think of that as a polygon area. And somewhere inside that polygon area, we can calculate what's called the centroid. That is the center X and Y coordinate for that group. And that centroid might be placed right about here for this 5-shot group. And then I can, again using the computer, calculate the distance from the centroid to each of these rounds. And then I get actually 5 measurements for this group instead of 1. And still, all of the measurements will be made in MOA. Now let me run through this with you on the computer, kind of explain the steps as we go. What we need to do is we need to acquire an X and a Y coordinate for each of the bullet impact holes that are in our target. Think back to when you were younger, taking geometry classes in high school or middle school or college for that matter, and having to graph those Cartesian coordinates, plot the X and Y coordinate on this piece of graph paper, and essentially that's what we're doing, but kind of in reverse. We have the points showing on our target, and now we need to acquire an X coordinate and a Y coordinate. And it doesn't really matter how we do that. I'm using a piece of software to do this, and as you see, I am clicking on the center of those bullet holes, and I can zoom up on those bullet holes and click very carefully on that. And by the way, what I did is I prefer scanning in those targets. Now, on a regular home scanner, you're probably going to have to cut the target to get it to fit, but you can do that. And it's better to use a scanner because then the paper of the target won't be rolled or folded or bent in any way. And so you're going to get what we call better registration. So ultimately, we get a set of X and Y coordinate pairs, and then what I'm going to do is I'm going to open up this distance to centroid calculation Excel spreadsheet that I put together, and I have simply imported, these are screen coordinates, I've imported these from the computer application into Microsoft Excel. By the way, you can even do this in an analog fashion, and it doesn't matter what those coordinates are in at this point. The screen coordinates, we're going to convert those things, part of this process, into MOA calculations. So I need to enter those X and Y coordinates or copy and paste them in, and I need to simply enter the MOA for that particular group. And you'll see that this does indeed look like that group that we were just looking at. Then the computer, Excel, is now going to calculate everything else for me. I've got a sum, I get a count of how many points were found, and then I get an estimation, or a calculation actually, of the centroid. And that is shown right here in the orange. Now in this Excel spreadsheet, the only data I'm entering is in this white area. Everything else in the gray is automatically calculated for me. Here's a point-to-point matrix. Notice that the point-to-point distance from point 1 to itself is 0, point 2 to itself is 0. That's kind of a double check to make sure everything is working correctly and has been entered correctly. The maximum distance happens to be this 1262.52. Again, screen coordinates, units are meaningless. That happens to be the point 1 to point 3 distance. And then this data is used to calculate the point to centroid distance. Again, these are still in screen coordinates. And then we get into the scaled distance to centroid. Now this is in MOA. The scaling factor, again, you're not going to modify this. This is calculated for you. This is 1,250. And what it is this value here, the maximum distance, divided by the known or measured MOA. And here we get the scaled distance to the centroid in MOA. And now what we have is we have 5 measures of precision for the one group instead of only 1. Now you might be asking, why do all of this? You know, I could just say, I think that's a flyer, throw it out and be on with it, right? Be done with it. Well, there's a couple of points I want to make about using this method. It is definitely more time consuming and it requires more effort than simply measuring extreme spread, converting it into MOA, and calling it a day. This method is not designed to replace that method. That method for measuring groups is a tried and true method, and I'm going to keep using it myself. Now, the reason why this method that I just described and explained with the use of the computer software is useful, however, especially in the case of flyers or possible flyers, as well as in the case of statistics and how we can analyze groups later on. Let's start talking about those possible flyers. You know, it's easy and it's done all the time for a person to say, that's just a flyer. I know I didn't pull it, but it's way out there, so it's a flyer. Well, what you might be doing if you do that, very much especially, is you might be kind of tricking yourself into thinking that, yeah, my favorite group, the one that I really like that bullet, I really like that load that I developed, it just does better than everything else. And oh, that round over there, that's always a flyer. It happens sometimes, but it's always a flyer. Well, you're kind of tricking yourself into thinking that you have a great group, or a great load, I should say. So let's look at it like this. Let's say that we're shooting 6 5-shot groups, and we're going to compare those results to another 6 5-shot groups, shot back to back with one another. That's indeed what we're doing with our annealing experiment in this season of extreme reloading. If the majority of the rounds impact with high precision, and then we do have one over here that we didn't call, and it's a possible flyer, if we keep that round in the group, we might be making another mistake where we accidentally choose a load that is not as precise, but maybe we don't see the flyers simply because they're more or less all flyers. And we're going to say, no, this one just, for whatever reason, is producing, the occasional larger group, so I can't go with it. It's not consistent. Well, this approach will allow us to identify those flyers and legitimately or justifiably kick them out of our analysis. So the approach that I like to take is to be as quantitative and objective as possible. I always say, let the data speak. And if none of the rounds exhibit characteristics of being a flyer, then I am going to keep those in my group calculations, and I'm going to live with it. This is really not a good group. Might be my favorite bullet, but it's not really doing that well, so I probably need to find a new favorite bullet. However, if this analysis, this methodology allows me to say, that really was extremely different, quite a bit different, substantially different than all the rest, I can kick it out, and then I say, gee, you know what? Over all my different groups I fired, this was the most precise group or precise load, and so I'm going to go with it. Now, as I alluded to earlier, this method is also very useful if we are going to be applying some statistical test to actually statistically or quantitatively compare one group to another, which we are going to be doing with our annealing experiment. And in statistics, sample size is very, very important. And as I said earlier, we're going to have 6 5-shot groups fired, unannealed in this case, and annealed versus annealed. That traditionally only gives us a sample size of 6 if our sample observation is groups. This method allows us to change that sample type from groups, 5-shot groups, into independent or individual shots, in which case I will have 30 shots unannealed, 30 shots using annealed brass. Now, if you know some things about statistics, and to be fair about all this, there is a rule that talks about the independence of observations, that all of those samples that you're calling valid samples need to be independent. While on one hand we can say those are independent shots. One shot was taken and it has no bearing on the subsequent shot or the shot before it. There is, of course, barrel heating and fouling and all this sort of stuff, and including shooter fatigue potentially and all this stuff. But we could say that for argument that each individual shot is independent. And there's a lot to that. However, the way that we're measuring this is dependent upon that centroid, which is calculated by all 5 of those shots. So we do not have perfect independence of observations. Now, to take care of that, because this happens so much when we're doing statistical analysis, there are 2 approaches to this. One is to use what's called a non-parametric test, a test that is robust to the violation of independence. And there are some tests we could use for that. The other approach is to increase the confidence interval, or actually decrease the confidence interval, so you do not accidentally accept a false result. In other words, instead of looking at 70% or 75% probability that this is different than that, we should be increasing that to probably 95% or maybe even 99% so that we do not accidentally accept a false result. Now that's the approach that I'm going to be taking to analyze these 60 rounds that we're firing for the annealed versus not annealed experiment. And by the time we're all done shooting all 60 of those rounds and analyzing those results by, number one, overall group size, traditional way of looking at things, this method where we're looking at the distance to the centroid, as well as looking at those muzzle velocities and the standard deviation of those muzzle velocities. With those three different measures and three different tests, I think we're going to be able to definitively answer the question, does annealing affect precision? Hey, thanks for watching. Have any questions, pop them into the comments below. We've got another range session coming right up in the next episode of Extreme Reloading.